So in this video and the next one, I'll look at how to carry out some standard regression analysis using time series data. Now, a lot of the techniques that I'll be using to estimate equations, of course, will be the same as in the videos I just did using cross-section data, but there are some specific feature-specific things that you need to do when it comes with time series data. For example, using lags of variables and first differences and so on. So begin by importing all the packages that we need. These are exactly the ones I used in the previous videos. NumPy, Pandas, statsmodels, Patsy are the four ones that we need. And these are the commands we need here. Again, these are just the same as before. So that's imported everything we need. Now, the data I'm going to read in is just a small time series data set with some some annual data on spending on output of the food, drink and tobacco industries in the UK. I'm estimating what would be called a production function. That is, again, the economics here is not too important if you haven't done this, but simply in a relationship where the dependent variable is output and the two independent variables are labour stock, the labour force used, and the capital stock. Now, I did read this in originally using this command here. Of course, it's the usual one, read_CSV. And what I did here was I included this option here, index_call, because the data set, the CSV file, does have a time index. It has years in the first column with the label year. And you can, if your data, your time series data already contains a suitable time index, you can simply use this option here to indicate that. However, and that worked fine. However, I found that later on when I tried to set up the Y and X matrices here using this dmatrices function which used previously, it didn't like it. So instead I created a time index separately using this function here that we looked at in the previous video. So I'm creating an index variable starting from 1960. There are 20 periods in my data set, and it's the frequency is yearly. So we saw how to use this date range function in the previous videos. So I've created this index here, and this is what it looks like. So the difference is when I simply imported the year variable, that simply has the year as the entry. So in other words, it simply says 1960, 1961, and so on. Whereas, as you can see in this index I've created here, it uses this format here. It's still annual, but it effectively gives the date at the end of each year, and that works fine with this dmatrix function and with statsmodels, but just putting the year didn't. Not quite sure why, but it didn't work, so I had to do this instead. So what I then do now, of course, is as I've done previously, I read the data in, and notice what I've had to do now is to exclude importing that first column where the years are. So what I've done here is use the use calls option here to specify that I just want the columns headed Q, K and L, output, capital and labour. In other words, it won't import the first column, which is labelled year. So I read that in just with those three columns, and then, as before, I use my index variable as the index of the data. So that is fine, that will work fine. If you have a quick look at it, you can see that it's got 20 periods, and of course these three variables Q, K and L. let's have a look at a quick plot of the data. This is a thing you'd probably want to do straight away, having imported your time series data. So I'm plotting a graph here of all three variables separately, hence the subplots equals true option. I've set an appropriate figure size. We've got a title. The layout is 3 rows, 1 column. So in other words, there'll be 3 graphs, one on top of each other, and an X label, and then showing it. So we've used this sort of function before with these options. So you see this is what we get. So that's by specifying a layout of 3, 1, we got 3 rows and 1 column. And subplots means that they're all in separate plots rather than having them all on a single chart. So there's the data. If you want some summary statistics, of course, use the describe function. Here they're all numeric, so there was no need to use that option include all. That was the option, wasn't it, if I remember correctly, that I've used previously. This does them all. This is useful just, of course, to check for any missing values. If the count should be the same for all three, it is. So that looks perfectly fine. Now, what you typically do, of course, with time series data, particularly in econometrics, which is what my main area is that you, rather than using the actual levels of the data, the actual values, you use the natural log. There are various reasons for that. Again, I won't go into the statistics or the econometrics here. I'm just indicating how to do these procedures in Jupyter. So here I'm going to create another data frame called LNDF, which LN standing for natural log. And I'm using the log function in NumPy, so np.log on my imported data frame. That will, of course, create another data frame where it's all the logs of the variables. What I then want to do is to relabel the columns with lowercase letters. I often, this is something you can do if you want to remember that these are now the logs rather than the actual values. If you kept with the capital letters, then you might think you were still dealing with the same data. So I think it's useful to relabel the columns. So here you can see I've just used the columns property here with an appropriate list. What I've also then created is a time variable, a time trend variable here, because I'm going to use that in this estimation here, because here I'm going to estimate what's called a ADF, a unit root test, augmented Dickey-Fuller equation. Again, if you've done time series analysis, time series econometrics, soon you'll know what that is. It doesn't matter, because I'm simply going to show how you can use the various operators here. But I need a time trend variable for that, so I've created that here. So we've seen how to add columns to a data frame. You specify the name of the new column here as part of the data frame, and then you give an expression to create that. So here I'm using the range function in Python to specify a range from 1 to 21. Actually, what that gives you is 1 to 20, because in Python, when you use the range command like this, 1,21, it goes to actually the one before the final, this number here. I'm not quite sure why. I probably did know why, but I can't remember. So in order to get 1 to 20, because remember I've got 20 observations, I needed to put 1,21. And then that range then has to be converted into a list. So you have the list function outside of it here. So you can see the syntax that you'd need to use if you wanted to create a variable just going from 1 to 20. So that's that. And if I now show the data frame, you'll see exactly that's what I've got. So here's my data frame now. There's that index I put in. Here are the logs, the natural logs with the new column labels. And here's that time trend variable that I created. As you can see, it's gone from 1 to 20. So If you want to know more about any of these functions, of course, you can put the cursor on and press Shift Tab, or you can go to the to the web page for pandas in this case. But hopefully, I think you can see what I've done here, so you could use this yourself. Okay, so there's my data set that I want to. So what I'm going to estimate, first of all, as I say, is a unit root test, an augmented Dickey-Fuller equation here. Now, again, the econometrics of this are irrelevant. I'm just simply showing how, with time series data, you often want to use lags and differences. That's quite common with time series data when you're estimating equations. So here I'm using this D matrices function again from Patsy, which creates, remember, these two matrices, y and x. The y containing the dependent variable, which would be quantity in this case, or log of quantity, and x, the regressor matrix. Here we've seen how to specify the formula for the equation you want to estimate, and then you indicate that where the data is coming from, and then you put return type. Again, if I did this in the previous video that I've just done, so you'll have seen that. So what I want to illustrate here was the use of the two functions here, shift and diff. Now, shift is the function you use here to lag a variable, and as you can see, you put the variable name dot the shift and then in brackets how many lags you want. So here I'm just creating the first lag of the L variable, and if you want the first difference of a variable, which remember is the difference between one value and what it was previously, then you use the diff function. Now in R, the function is called lag, which I think is a bit better, because that's typically what you call such a variable, a lag. But here in Python, in Jupyter, in pandas, it's called shift. Diff, however, I think if I remember correctly, in R, that's the same name as using R for a first difference diff. So that's a bit better. That's a bit more explanatory. So if you want to create a first difference, use the diff function like this here, to the variable name dot and then diff and then in brackets. If you just put brackets on their own, you get the first difference. If you want the second difference, put a 2 and so on. And here's what you do to get a lag. So here, notice here, what I'm finding is the second lag of the first difference. So notice how you put the functions together like this using the dot notation. So it's L, because I'm doing it on this labor variable. Then firstly diff, and then dot shift. So as you can see, that's going to create the first difference, which is then lagged twice. Okay, so if I run that, we'll get those matrices, and then I use these three familiar commands we saw before to actually estimate the equation and get the results. We get a little warning here because of the small sample size, that the kurtosis value here is only valid for n greater or equal to 20, and we've only got 17. Remember, of course, that when you start lagging variables and so on, you lose observations. So although we had 20 in our data set, by the time it's created these lags and so on, and these we ended up only with 17. I'm not interested really in the kurtosis value here anyway, so it doesn't really matter. But that's perhaps worth noting. So that's how we can use the shift operator, the shift function, and the diff function to create differences and lags, which, as I say, is typically what you often do with time series data. Now, having got the results, of course, we would want to check for any problems with the residuals, because they check that they're random, that we haven't got any particular problems. Of course, the problem that often occurs with time series data is autocorrelation, is some relationship between the errors terms as indicated by the residuals. Now, there are various ways you can test for autocorrelation. One thing you can immediately do is to look at a plot of the residuals. So here I've done that. Again, this is stuff I've done before. So remember the resid property contains the residuals of your estimation, and then you just put the plot function, and plot on its own by default gives you a line graph, which is what I want. So that possibly suggests some pattern in the residuals, but of course it's not clear cut. Another thing that you could look at, of course, is the ACF, the autocorrelation function, or the graph of the autocorrelations as an indication. So you can do that here using this function in statsmodels, graphics.tsa.plot_ACF. So it's in statsmodel, so it's sm dot and then this function here. And that takes two parameters, the residuals, and then how many lags back you want to calculate the autocorrelations. So here we get the autocorrelation chart nicely. You notice we're getting these in the ggplot style because I'm specifying that at the beginning, of course. And as you can see, there's no indication of any significant correlations there. They're all within these bands. This one, of course, is 1 because that's a correlation with itself. You don't actually need that, and some charts, for example, in R, it doesn't give you that first one because it's always 1. It's from the first lag onwards that we want. So that's looking okay. Of course, another way to look at this is to look at the Leung box statistics, which tests whether a subset of these autocorrelations are jointly equal to 0, are jointly not significantly different from 0. So you can do that here with this function again in stats models. So it's sm.stats.acore_Leung box, if I'm pronouncing that correctly. And here you just put the residuals, comma, and then how many lags you want to look at. So I've just put 4 here, and we get the statistics with the p-values. So we're looking for any here that are less than 0.05. None of them are, so again, not indicating any problem autocorrelation. Finally, of course, you could look at calculate the Breush-Godfrey statistic, which is the standard test for autocorrelation. It's essentially it's a Lagrange multiplier test, essentially a large samples test. So here the sample's a little bit small, but this is available again in stats models with this function stats.acore_Breush_Godfrey. Again, 2 parameters here. There is you put the results. Notice you don't put the resids here. You have to put the actual variable containing your results, res. That was where I stored my results, if you remember, here. And then a comma, and then what degree of autocorrelation are you testing? First order, second order. So here's first order. We get the chi-squared statistic here with the p-value. This one here is I think is an F value, which might be more appropriate, a small sample, but I tend to look at the chi-squared one. Again, that's suggesting possible autocorrelation. It's just slightly below 0.05, the p-value. If you want to look at second order, just put n lags equals 2. And that one is just about okay. So that's looking just about okay as far as having no autocorrelation in.